building. As it's coming down, now the second wave starts coming. This is called dynamic pressure, and it is usually slower and it takes more time to reach the building, but the combination of that gives you the shape that you have seen. These schematics represent that. First the shock wave comes, it reflects, and then dynamic pressure comes. So we have to deal with incident pressure, reflected pressure, and dynamic pressure. These quantities are referred to as blast parameters. And that's why you have this bilinear idealization instead of hyperbolic relationship that I showed you. So what happens is that this is the incident pressure, and then it reflects, goes up to reflected pressure, and then reflected pressure starts dying down, and it clears its effect from the sides or from the roof. This is called clearing distance. T sub C is T clearance. But then the other pressure, which is this pressure plus the drag effect, because when the gas pressure comes, it engulfs the building. Depending on whether it's a circular building, square building, there's drag coefficient. So drag forces are generated, it amplifies a little bit, and then it starts coming down. So this shape can be used to more accurately idealize the hyperbolic pressure-time relationship. There's another important aspect of blast pressure. I have given you the impression that pressure is probably the only thing that matters. That's not true. Impulse is another effect that affects building performance. So pressure and impulse. Impulse reflects duration of pressure, which is the area under this curve. Pressure versus time. So area under this triangular or bilinear relationship gives you impulse. Impulse is very important. In fact, if you go to extreme impulse, which means if you make this horizontal axis very long, then it becomes impact. Impact factor in engineering, we usually use about 2, right? If you apply same load statically, you may get P. If you do it very quickly, if a car impacts a building, then you multiply it by 2. But that impact, even though we think it's happening very quickly, it takes place over some time, and that time length is very high relative to shock waves. Shock waves are in milliseconds, impact is in seconds. So this is why duration of pressure is important. Okay, so now we learned that charge weight is one parameter, standoff distance is another parameter, and they result in reflected pressure, and this reflected pressure takes place over a certain time. Now let's idealize these factors so that we have workable scenarios. And after all, we're structural engineers, we want to know building response. And these are the idealizations. Often, what we do is we find out what is the reflected pressure and duration and impulse. So if I take impulse multiplied by 2 divided by duration, and that gives me, divided by pressure, that gives me duration. In other words, I find time such that area under actual distribution is equal to area under the triangular linear distribution. This is idealization, and we almost always use triangular distribution, right? Blast effect is such a low probability rare event. We don't want to split hairs. We don't want to give undue accuracy because we don't know whether it's 200 or 250 kilogram threat that we're going to face with. It doesn't make sense to try to integrate parabola, hyperbola, although in my graduate class I make students do numerical integration as an exercise. But in design problems, we deal with these idealizations. So the one on the left-hand side is for front loading. The one on the right-hand side is side loading. But notice that in side loading, we don't use reflected pressure because nothing is reflecting. It's parallel to the blast pressure. And similarly, roof loading has this kind of a shape. And rear wall loading, there's some delay by the time shock wave travels and goes to the back of the building. There's some time delay, but other than that, these are the blast parameters. So how do I now go from charge weight, standoff distance to obtaining these triangles? Okay. To do that, we use scale distance because there are too many parameters. But Hopkinson-Kranz scaling law says that scale distance, Z, relates to standoff distance and charge weight through this equation, which means if I increase standoff distance by a factor of 2, I have to increase charge weight by cube to get the same effect. So as you can see, only increasing standoff distance from 10 meters to 20 meters, now I have to increase charge weight cube of the first charge weight to get the same damage. So this is very important. That non-dimensionalizes things. So I don't need to come up with design charts for 100 kilogram TNT, 500 kilogram TNT. I can come up with non-dimensionalized term, which is referred to as scale distance Z. Now, if you know Z, then U.S. Army, it was a classified information, but they released it. They have done a lot of actual explosions, and they came up with empirical curves. So as you can see, these curves look very funny because there's no closed form equations behind them. They're just plotted as average values from their explosive tests. U.S. Army released this for the benefit of structural engineers, civilian engineers. So in this, they have different charts for TNT in free air and TNT in hemispherical ground surface, depending on your shape. They also have curves for inside explosions. But if you enter with Z, let's say Z is 1, and depending on which curve you interact with, dotted line gives you reflected pressure, dashed line gives you incident pressure, and then dashed solid line gives you impulse. I stands for impulsive reflected impulse. So once you get these quantities, then you are ready to establish parameters of those triangles. So those triangles form my load. Alternatively, you can use software. This is a software that was developed by a PhD student, which is quite commonly used throughout the world now. And there was another software called ConWeb, and this was disclosed by U.S. Army earlier. So all you have to do is enter here TNT weight. As you can see, this is 200 kilograms. Place that standoff distance of 30, and then there's angle of incidence. Usually it is taken as 0 if it's right in front of the building, but if there's angle, if you want to find pressure on third floor, then it goes with an angle. The effect decreases. In this case, angle of incidence is 0. So now on the right hand side, you come up with incident pressure, which shows 41 kilopascals, and then impulse is 338, which is the area under that black curve, and then reflected pressure is indicated with the red curve, and here you have increased values 93 and 570. So if you have the area, you have the pressure, you set that equal to triangular area, solve for duration, you have all the parameters. You're ready to now exercise your structural engineering knowledge, right? We're done with explosives and security engineering part. Okay, so once you have this load, what do you do? What's the difference? We're all familiar with earthquake engineering. We'll be discussing this afternoon. But in earthquake engineering, you do not apply any load on the building. You just shake the ground, right? So when ground shakes, you induce accelerations. Mass of the building, which usually concentrates at floor levels, causes internal inertia forces. So in earthquakes, forces are internally generated inertia forces, and those forces are resisted by the entire building because mass is distributed, the whole building responds to it. And as you know, there's a very delicate relationship between the frequency of the structure and frequency of excitation, Right? If you have a high frequency earthquake, let's say the building is located on solid rock, then it will do this. This is the earthquake frequency, and if your building is reinforced concrete, 2 stories, shear walls, very rigid, your building also has this period. So if periods match, as you all know, there's a phenomenon called resonance occurs. So a period of excitation, which means period of earthquake, approaches to period of the building, seismic forces increase. Theoretically, if they're equal, it goes to infinity, right? It never happened that in real life, but periods are related. So if you have a very long period earthquake, as in the case of 1985 Mexico City earthquake. Mexico City is built on previous lake, right? And there's a legend about that, and according to Mexican legends, and Incas wanted to establish a town, and they used to believe that gods would tell their birds to tell where people should live, and birds were all going into that on top of the lake, so they decided to build a city. And eventually the lake dried out, they filled it, so it's all reclaimed land. This is all to say that soil is so soft that it has very long period. When there's an earthquake, this is what the soil does, right? And if you have a 2-story building, this does that, so they don't talk to each other. Low-rise buildings, nothing happened. But they started developing high-rise condominium complexes. Buildings about 20 floors started falling down. They couldn't understand why, because they had long period, excitation was long period. In September of 2017, I was in Mexico again. There was another earthquake. This time, the former lake region survived, and then there was a transition zone between the hilly location and the former lake region, and this time 10-story buildings started falling apart because the earthquake frequency characteristics was such that frequency of excitation was about 1 second, and 10-story buildings have frequency of 1 second, so a period of 1 second. So then they started damaging this 10-story buildings as opposed to 20-story buildings that got damaged in the central part of the city. So this is very important to understand that period of excitation and period of the structure are closely, intimately related. When we come to blast engineering, period of the entire building is too small as compared, or frequency is too small, period is too long relative to the period of blast phenomena. I said periods or durations are expressed in milliseconds, and period is the time required to complete 1 cycle. So that triangle completes half a cycle. Multiplied by 2, that gives you period of excitation. Period of excitation is measured in milliseconds. Now the building period is measured in seconds. So the entire building is not affected because they don't talk to each other. But if you look at period of a facade, if you look at period of a column, they have very high frequency, low period. So now period of excitation starts affecting facade elements, not the entire building. And that's why I've shown you all those pictures. The facade came down because these are the high frequency members of the structure that are influenced by blast loading. So what do we do in earthquake engineering? Obviously we do multiple degree of freedom analysis. If you have a 5-story building, you have 5 degrees of freedom. Although we simplified it and use single degree of freedom equivalent static load approach. But in blast engineering, life is even simpler because usually single degree of freedom analysis gives you fairly accurate results because these columns bend in one mode, right? They bend in half sine wave deflected shape, and so all you have to do is do single degree of freedom analysis. So what does that mean? Dynamics is a big word. Some people are scared, but it's really very easy. This is the equation of motion, which means dynamic equilibrium equation. If you don't see U double dot, which is acceleration. Then you have static equation. Right hand side is applied force.